Okay. As Bob mentioned, this is part of an ongoing joint project with Adrian Clingher and Andreas Malmendier. And so we already have essentially produced the first paper in hopefully a series, and this is about the second one. So, but in all cases, the goal is modular parameterizations of lattice-polarized K3 surfaces. And more explicitly than that, is to calculate the coefficients of Weierstrass equations for these K3 surfaces in terms of modular forms. So this is by now a fairly old subject. There's a lot of history about like explicit K3 surfaces. I think probably the first person to work on this was Inose, who described explicitly a family of K3 surfaces in terms of what's called the Inose quartic. But more in the spirit of what I'm trying to do is some papers by Clingher and Adrian, which there's at least in 2007 and 12. Like Iwata and Shiona, Nagano, and Nagano Shiga. And here there's actually quite a lot of papers they've written on the subject, and just trying to write. They've been doing this for about a decade or so. And what these mostly have in common is that they produce results for K3 surfaces with relatively high Picard rank. So for example, this would be, let's say, Kummer surfaces. And so Clingher and Adrian, for example, have considered Picard rank 18 and rank 17, and they compute explicit models for these K3 surfaces where the coefficients in the Weierstrass equation are given by Ziegler modular forms. What I want to do is actually extend that to Picard rank, which is quite a bit lower, which in turn means the number of moduli is higher, and in some sense makes the problem a priori more difficult. And we do this by using a kind of different method to the previous papers that I mentioned, and I can motivate this in terms of elliptic curves. So we know that the moduli space of elliptic curves for A1 is the complex upper half space modulo SO2Z. And over A1, there's a universal elliptic curve, which we can put into Weierstrass form. As follows. So a short Weierstrass equation in which the coefficients depend on tau in the H, but also actually modulo SO2Z. And if you actually work through the definition, what these coefficients represent, you'll find that they represent classical modular forms in the sense of modular forms for SL2Z, but weights 4 and 7. This belongs to M4 SL2Z. This belongs to M6. And it's known, or at least I'll assume it's known, that this implies that A4 and A6 are some multiples, constant multiples of the Eisenstein series. Here Q is e to the 2 pi tau. Sigma k is the divisor sum. And similarly for A6, we know by the fact that it's a modular form what it has to be at least up to a constant. And these constants are not completely fixed, but they are fixed up to, in the sense of element of weighted projective space. So we're allowed to multiply A by some 4th power of a complex number and B by some 6th power of a complex number without changing the elliptic curve. But that's it. Anything else would change the elliptic curve. How do we figure out the coefficients A and B? Of course, there's many ways to do that, but I think the easiest way to do it is to take the discriminant with respect to x, which is given by minus 4a4 cubed minus 27a6 squared. And note that this is never 0. So this is some modular form of weight 12, which is never 0 on the upper half plane, and that forces it to be a multiple of the famous delta function. In particular, the constant term of this thing has to be 0. And so, without loss of generality, the easiest way to solve this is by taking A equals -3 and B equals 2. And that's our answer in this case. And of course, there's various generalizations of this that you can do for curves. I want to do a kind of similar argument for surfaces. So in our work, we draw the elliptic curve.
So I can ask a dumb question maybe.
Sorry,
So every time you include the saying this is a modular form of this weight, and then that has to be a multiple of E4, E6, or that one?
Yes.
So the modular forms of a given weight are all vector spaces of dimension 1, at least for 4.
Sorry. So, okay. Yeah, so this argument, of course, relies on knowing the structure of modular forms in the first place. That's also going to be true for the rest of them. That is a good point. So here it's known that if you take modular forms of any weight, that's exactly the polynomial ring in E46. But you don't need to know anything about elliptic curves to prove this. You can prove this by complete, again, naive arguments. So this is not circular.
So that is graded with E4 graded
Graded by the weight.
And degree 6.
Yeah, E4 weight 4, E6 weight 6.
Yeah.
Weight 12, it's dimension 2. However, this function is distinguished by not having zeros.
Okay.
That's the point.
Thank you very much.
Yeah. And so you can do something similar for example, if we take elliptic curves with a marked torsion point, maybe it's worth mentioning. Say, that's the general elliptic curve with a 2 torsion point at the origin. We can do the same thing with a 3 torsion point at the origin. These are modular forms of level gamma 1, 2, level gamma 1, 3, and you can pick them out. Again, essentially by knowing what the role of the cusp is. So here there's a compactification where you can actually add in somehow the point at infinity that corresponds to an elliptic curve with a node. Here there's 2 cusps. Either the node is on the marked point or it's not on the marked point. You can figure out which one is which by working out the coefficients, and yeah, so it's kind of fun. Anyway, so we tried to do an analog of this, but instead of elliptic curve, we have a Jacobian K3 surface. This modular space A1 is replaced by the orthogonal modular variety. The Eisenstein series, E4, E6, these will be replaced by the so-called Gritsenko lift of Jacobi forms. The role of the cusp, infinity, where this function actually does vanish. The role of the cusp is now replaced by what are called the Noether-Lefschetz loci. And the role of the function q times product q1 minus q to the end of the 24, which we compare coefficients against, is replaced by what we call Borch's product. So I'm going to try to, I guess, explain a little bit about what all these things are, and then hopefully describe what our actual results are. So essentially, modular forms are going to be replaced by Jacobi forms, and modular forms are more variables. What is a Jacobi form? So it's easiest to describe in index 0. Here a meromorphic function from h times c to c, h is the upper half plane, is called Jacobi form of index 0, and with k if it satisfies some kind of modular transformation law. So with respect to the variable tau, it's almost modular, except it has this additional cocycle in the z variable. That's for A, B, C, D, and SO2Z. And if it's for fixed tau, it's going to be periodic with respect to the lattice described by tau. So the most familiar example, which we'll also have to use, is the Weierstrass elliptic function. This long definition, d plus n tau plus n squared minus 1 over n tau plus n squared. And this is known to be an elliptic function, and it's also satisfies this homogeneous property with weight k equals 2. K equals 2. And I normalize it. So that it has a nice Fourier expansion. Right in this form. This, I think. E times zeta to the minus d minus 2 plus zeta to the d, 2 to the n, where d runs through the divisors of n. And here the notation for Jacobi forms is always q is e to the 2 pi I tau, zeta is e to the 2 pi I z. And in general, Jacobi forms are supposed to describe the transformation of theta functions and not just elliptic functions. So the theta function, and the one I use is called the odd theta function. There's essentially 4 classical theta functions, and only one of them transforms correctly under the full group SL2Z. You can also write this in following form, q to the 1 over 8 and zeta minus 1/2 minus zeta 1/2 times the product from n equals 1 to infinity, 1 minus 2 to the n, 1 minus 2 to the zeta, 1 minus 2 to the n, zeta minus 1. This is the Jacobi triple product. This is supposed to be essentially the fundamental Jacobi form of non-zero index. So it satisfies, well, let me maybe not write it out in too much detail. There's a theta transformation formula. Some root of unity times square root c tau plus d and so unfortunately, these formulas somehow look very strange. I guess if they're not familiar, it's kind of hard to justify why they look the way they do. So we have some kind of twisted modularity with respect to tau and with respect to the elliptic variable. It's also not exactly periodic, so there's some factor depending on m and n. There's also some exponential factor. Anyway, so it's this function. Yeah, this function satisfies some kind of modified modularity and some kind of modified ellipticity. And we simply define this to be a Jacobi form of weight 1/2 and index 1/2. And we say F is Jacobi form of weight K and index M if the quotient F divided by theta to the 2 is Jacobi of weight K minus M and index 0. So not a terribly satisfying definition, but that's, I think, the most efficient way to get it. Any questions so far? Yeah, so these are some special functions that have essentially been around in some form or another for probably what will soon be 200 years. What we actually use is so-called Jacobi forms of lattice index, which is a bit more modern. For this, I need for L to be a positive definite even integral lattice. So it's essentially z to the m, and it has some integer valued bilinear form on it, such that the square of any vector is even. And a Jacobi form of index L is going to be a function which takes vectors in L with the following property. That if you evaluate it along any lattice vector, this is a Jacobi form of index on the square root of 2. Yeah. Okay. The main example I want to consider so these are the two root lattices from the title, Dn, which will be vectors from z to the n, such that their sum is even. And inside of that, we have a n minus 1. Where this one is 0. So I don't Jacobi form of index not 1, sorry, A1. That's a function of the following form. So elements of A1 in our notation are complex pairs that sum to 0. So this is some function of the form f tau comma z minus z. And that's exactly the same as a function f tau comma z of classical index 1, so Jacobi form of index 1. And we have certain special functions. The first one, which is called phi minus 2, 1, is eta squared divided by eta to the 6, where eta is the 24th root of delta. So eta cubed is exactly the 0 value of theta derivative at z equals 0, which tells you that the roots of unity that were involved in this definition cancel. You get something of weight minus 2 index 1. We also have phi 0, 1, which is the same thing after multiplying by this normalized Weierstrass p function. And here it's a theorem due to Antwerp and Jacobi from 1985. That these let me not write it like this. We generate the module. It's a module over the ring of modular forms of so-called weak Jacobi forms. And weak means that you have no negative coefficients in the Fourier expansion, or no negative exponents in the Fourier expansion. For modular forms, that would be the same as saying it's a holomorphic. That's the notion of holomorphy at infinity. For Jacobi forms, it's actually not the correct notion of holomorphy. But so this was proved, and that essentially is Jacobi forms of index A1. And we have the following generalization. Which is due to Gartola. And that's the following. So suppose I have a vector from AN times C, that just means the sum of the entries is 0. We define these Wronski determinants of the Weierstrass p function, which means we take the determinant of the following matrix. The first column is all ones. The second column is Weierstrass p evaluated at any n of these entries. Say we omit Cn plus 1. We take the nth derivative And this is not square, so we have to omit some column. So say I omit the kth column from this matrix. Let me take the determinant of that. With theta tau comma z, the theta block is going to be delta to the minus n plus 1 over 4 times the product of the Jacobi theta function evaluated at the n plus 1 entries. And then we define the following quotients. And the theorem is that these generate the module of weak Jacobi forms of index an for any n. Okay. Yeah. So there's a lift to modular forms on orthogonal groups. I want to be a little bit vague about that, since I don't think if I say too much about this, I'll run out of time. But so briefly, if you have a lattice not positive definite, but now of signature 2, n for some natural number n, there's a complex structure. There's a Hermitian symmetric domain attached to that, and there's a notion of modular forms. Here, the lattice that I'm going to consider is 2 copies of the hyperbolic plane. So U is Z2 with the geometry 0, 1, 0. And I take the same lattice that I had from before, but multiply its bilinear form by -1 to make it negative. There's a notion of modular form on this. There's like a legitimate definition of modular form for this, but the way you can think about it is in terms of a Fourier Jacobi expansion. So a modular form on here is always something of the following shape. Each Fn is a Jacobi form for the lattice. Same lattice L, but now with its bilinear form multiplied by n. And of course, it has to satisfy some additional conditions. Because Fn's can't just be completely random; they're all compatible with one another. But there's a lift that takes a Jacobi form and produces such a modular form in a pretty canonical way called the Gritsenko lift. and it has the following basic structure. It takes F and sends it to the series F/Vn, which means it applies a Hecke operator. Very much analogous to the Hecke operators on modular forms, but somehow the action on the elliptic variable is such that it raises the index. There is such a Gritsenko left. So now that I have these special Jacobi forms, I can define some special modular forms. And there's a theorem. This was proved by Haoru Wang and myself, 2020, that for 1 listening with n listening to 7, the algebra of modular forms for the orthogonal group, more precisely the discriminant kernel. I don't want to explain the difference too carefully. It's kind of index 2 in the orthogonal group. There's a polynomial algebra on certain Eisenstein type generators called E4, E6, even though it's a little bit dubious. But some modular forms which behave similarly to the Eisenstein series, and then these forms chi 12, chi 10, down to chi 11, with no relations. So the modular forms have no relations. One example, for n equals 1, the orthogonal group of A1 is essentially the symplectic group SP4. There's an isogeny. And this is the structure theorem of Igusa in this case. These are actually exactly the Igusa forms which are traditionally called chi 10 and chi 12 in the Ziegler modular forms literature. There's technically an extra weight 35 form also that actually doesn't appear. That's why the equals is in quotation marks. This group doesn't admit chi 35. Well, SP4 doesn't. Okay. These are ultimately going to be the things that we try to express the Weierstrass equations in terms of. If you want to say for finding explicit Weierstrass equations, you have to have some explicit forms in the first place, and that's what these are.
One question: what do you mean by they behave similar to Eisenstein series?
Yeah, so Eisenstein series is somehow something that only converges if the weight is quite a bit higher than the rank of the lattice. However, one possible definition of being an Eisenstein series you could have is, first of all, it's not a cusp form. Second of all, it's image under a particular Ziegler phi operator, or down to genus 1 modular forms is also the Eisenstein series, and that's actually what it represents the Eisenstein series under Ziegler phi.
Then I think you can also write them using this Hecke trick. given this extra spectral parameter S, and we should end up with the same Eisenstein series.
It's possible. For A7, it's tricky. I think weight 1/2 Eisenstein series is difficult. Anyway. Okay, let me talk really briefly about K3 surfaces. So you look at an elliptic surface. That is going to be a smooth, complex projective surface X together with a proper map onto P1, for which the general fiber is a smooth curve of genus 0. Sorry, genus 1, what am I saying? And by Jacobian surface, I mean an elliptic surface that also admits a section such that the generic fibers are actually elliptic curves. Generally, some fibers are going to be singular. You can't always get smooth genus 1 curves. If you did, the fact that this thing is proper and you got J invariant means that it's going to be constant here, and that's not very interesting. So there's going to be some singular fibers. The singular fibers generally have more than one component. Like the section, the others will not. And constructing the components that do not meet the section, you obtain a singular surface, which has a flat proper fibration to P1, and is actually given essentially by the usual Riemann-Roch style computation by some Weierstrass equation of the following form. Where these are sections of some bundle, or like sections of a power of some bundle in P1, that literally just means they're polynomials. And they're polynomials of degree less than or equal to 2D, 4D, and 6D respectively, where D is called the degree of the surface. So the classification of such surfaces, D equals 0 is isotrivial. Equals 1 is a rational elliptic surface. So here it's just elliptic curve times P1. Here it's a rational surface. D equals 2 is K3, that's the one we care about. And D equals 3 is called properly elliptic, and there's not much I can say.
So is that the definition of the degree of x, or is this a property of the degree of x?
It's a property of the degree of x. So the degree, what you're supposed to do is actually take the normal bundle of the section and pull it back to x, and then, pull it back to P1. So that'll be L inverse for some bundle L on P1, and L has some degree, and that degree is called the degree of x. So in the degree, in K, the K3 case, here we know the large numbers of the surface are as follows. H2 is an even unimodular lattice of signature 319. There's essentially only one sublattice. So we kind of fix a representative of what we say 30 plus 2d8 and 1. And for such a K3, the Picard lattice belongs here. And so it has rank 1, comma, rho minus 1. Where rho is called the Picard number. And Tx is the perp, the orthogonal complement within lambda K3 is called the transcendental lattice. The reason this is related to modular forms is because we have the Torelli theorem, which you can state as follows. Suppose I fix some sublattice S with rank 1, R, and I look at lattice-polarized K3 surfaces, which is in some sense pairs of X together with a nice embedding of S into the Picard lattice of X. And the Torelli theorem is that the orthogonal modular variety attached to the complement of S is exactly a period domain. For polarized K3 surfaces. Yeah. So where does S come from? Generally, there's by a theorem of Shioda and Tate, there's essentially only two sources of the Picard lattice. One is singular fibers. Each singular fiber has some contribution to the Picard lattice depending on its Codiro symbol. And two sections. So the singular fibers each contribute root lattices. They span what's called the trivial lattice in the Picard lattice, And it's a theorem of Shioda that the quotient by the trivial lattice is precisely the Mordell Weil sections of vibration. So what that means in particular is that the neutral Lefschetz loci, which is the locus inside of here where the Picard lattice is not just S. It's somehow, there's extra curves. Those can be described by collisions of singular fibers, or they can be described by imposing the existence of sections. Okay, so let me actually say what we proved. So first of all, the following Weierstrass equation, and it's a bit hard to say exactly what's going on in symbols, but I think I can maybe explain it in words. So U is going to be our variable that lives on P1. So this is what I call A2. Recall we have V equals 2, so this is actually a polynomial of degree 4. You think of it as a homogeneous form of degree 4. X squared plus this is the A1 case, and then I extend it to higher Picard, actually lower Picard ring, higher AN, by adding on terms as follows. So this is now the case A2. For A3, I now raise the degree of this by 1. For A4, I raise the degree here by 1. That's A5, A6, and finally A7. This describes a family of K3 surfaces. There's some discriminant conditions like the F4, F6, and so on can't all be 0. Some conditions, and the very general member has transcendental lattice 2U plus AN minus 1. And the coefficients F4, F6, GK, HK, they generate the algebra of modular forms with respect to T. So we recover the result I proved not using K3 surface techniques. And finally, if we get explicit expressions for F4, F6, and all of these coefficients, Fi, Gi, Hi have explicit expressions, we can actually write them down in E4 E6 and the generalized E-group forms. For example, let me write the first few. F4 is minus 3 E4 minus 290304054. This is 2 to the 10 times 3 to the 4 times 5 times 7. G4 is minus 72576 So 12 to the 4 times 35. I don't have a particularly good explanation of why these factor into relatively small primes. H5, you actually have to add a square root, but that's okay because we're squaring it. Should be that's fine. F6 is 2E6 plus 41471356. Again, nice number, and etc. So we can actually write these coefficients down, and they are essentially unique up to some single common rescaling relative to the weight. So I'll do a brief explanation of what our argument looks like in the case n equals 1. I should say the second family in the title, I'm not going to write it down. It is associated to the Dn family of root lattices, and the results are fairly similar. What does our argument look like here? We have the following equation. We call this P of x. When I look at the discriminant with respect to x of p, that turns out to factor in the following form. We have this quadratic factor splitting off times some polynomial of degree 6. If I look at the discriminant now with respect to u of that polynomial of degree 6, that's some expression of the coefficients, and it happens to be of the form, it's a holomorphic square. So it's some expression in the coefficients which I know are Siegel modulo forms. This is actually the Clingher-Doran case. This is previously known. I know I can take a square root, but the result is no longer in this form. And from the known structure of Siegel modulo forms, you can figure out that this has to be the following function up to a constant. Because there is no other expression in weight 60 which has a holomorphic square root, and that square root is not a Siegel modulo form. So it has to be this. Chi35 is some construction by Yagusa in terms of theta constants. Chi5 is like a product of theta constants. For this, we know a Fourier series. We know that F4, F6, G10, G12 belong to a finite space of possible Fourier series. And this equation turns out to just compute them uniquely in one single go. And that's the argument in this case. The argument in the general case is more involved. We not only use collision of fibers, which is what this describes. This is when two fibers with the Kodaira symbol I1 collide to a fiber of Kodaira symbol I2. We also have to impose sections, consider forms that vanish on neutral Lefschetz loci, but in principle, yeah, as you see, we get the answer. It's a thing called a